Alright, so this is our final video on determinants for Chapter 7. This is on a result known as Cramer's rule. This is an application of determinants. And this gives us a method for solving systems of equations using determinants. It's a method that only works in the case where you've got same number of variables as equations. So let's say three equations, three unknowns, where there's a unique solution, right? So it's not as universal as the methods we looked at earlier in Chapter 5. It's also not as efficient as the methods we looked at in Chapter 5, but just like the determinant formula for the inverse, it does have its practical applications. And Cramer's rule, this is a method for solving systems that predates the Gaussian elimination method. So this is an old method. So it applies, like I said, when you've got n equations and n variables, same number of equations as variables. One of the things that we know is that if A is invertible, we can solve for the column vector x here by multiplying both sides of the equation by A inverse. And we also know that we can now write the inverse using this adjugate formula, adjugate of A times 1 over the determinant. And that means if we wanted to, if we want to know what is xj, well, xj, that's in row j, and how do I get sort of the row j entry from a matrix product? Well, I take the row j from the matrix on the left and I multiply by the column b. That's what's going to give me the jth entry, right? Is the jth row of the adjugate times b. Okay, so this is essentially Cramer's rule, but what we have to do is say, well, what exactly is row j of the adjugate? What does that look like? Right. So row j of the adjugate, that's going to look like, right? It's going to look like the sort of so it's going to be the cofactor. So it's going to be the 1j cofactor. Down to the nj cofactor, right? Because remember that row j of the adjugate is column j of the cofactor matrix, and then we do b1 down to bn, and when we multiply those, we get b1 times cofactor a1j down to bn cofactor a j, which looks an awful lot like a cofactor expansion for a determinant. It looks an awful lot like a cofactor expansion along the jth column of a matrix. And in fact, it would be like doing the cofactor expansion along column j of our matrix A, except that the numbers out front are now b's instead of a's. So basically what you're computing here is the determinant that you get if you take column j from your original matrix and you replace it with these numbers over here on the right. Okay, so you take one of the columns in your matrix, you replace it by the column vector on the right hand side, and you compute the determinant. So that essentially is Cramer's rule. Okay, so we let A sub I be the matrix that you get if you choose one of the columns, column I in this case, and you replace that column by this column vector b on the right hand side. Then you compute that determinant and then you divide by the determinant of A. Okay, that's Cramer's rule. So it gives you a formula for each of the variables. It gives you the value that each of the xi's must have in order to solve your system. Okay, so this can be useful again in situations where you're trying to solve a system, let's say with variable coefficients, something like that, where it's not very practical to use Gaussian elimination. But if you're just dealing with a system with numerical coefficients, especially with integer coefficients, this is not going to save you any time. It's a result which is probably more useful sort of theoretically or in other areas of mathematics than it is for sort of these sort of computations that we do in a linear algebra course. Okay, so for example, here's a system. And I'm just going to bother to solve for y, right? You can do x and z on your own time. Let's see, we want to solve for y. So solving for y means I need to form this matrix A2. Okay, So my coefficient matrix is 2, minus 1, 3, minus 3, 4, 2, 4, 0, minus 5. So the matrix A2 is the matrix I get if I replace column 2. So the first and the third columns remain the same. But the second column I replace with these numbers on the right hand side. 2, minus 3, 1. Okay? So now I calculate the determinant of A2. And how do I want to do that determinant? Let's expand along the, I could do row operations, but it's 3 by 3. Let's just expand along column 3. 4 times the determinant minus 1, minus 3, 3, 1. So 4 times minus 1 plus 9. Well, let me put the other one in. Then we have minus 5 times 2, 2, minus 1, minus 3. So, minus 5. Minus 5. So I get this minus 5 times minus 6 plus 2. So that's going to be 4 times 8, 32. And then this is going to be minus 5 times minus 4, so 20. So I get 52. The determinant of A, we can do that one as well. Let's expand along that same column. 4 times minus 1, 4, 3, 2, minus 5 times 2, minus 3, minus 1, 4. So I get 4 times minus 14, minus 5 times 11. So that is minus 56, minus 55. Ooh, boy. So minus 111. Well, here's maybe a case where it's probably good that we use Cramer's rule, because what is my y value? Again, check my arithmetic. I might have messed up. I'm getting a y value of minus 52 over 111. Probably we wouldn't be very happy if we were doing that by hand. And again, check to make sure I didn't make any arithmetic mistakes here. I think it looks reasonable, but you can double check my answers.